Welcome to this podcast, Road Science, created by Juan Fernando Aguirre Lopez.
Félix Ordóñez Sánchez.
Paulo César Pérez Yaguana.
In this occasion, we are going to talk about pavement design factors. Now, relax and let's go to the trip. These factors are divided into four broad categories: traffic and loading, environment, materials, and failure criteria.
For the first category, we talk about in four different topics. For the pavement analysis, the wall base of a typical semi-trailer must be considered as a primary factor. It consisting of a axle with single tires, single axle with dual tires, and tandem axle with dual tires.
And what happens if the spacing between two axles is too much? What about 4 or 7 meters?
It have no effect on pavement designs because the walls are so far apart that their effects on stresses and strains should be considered independently.
In this sense, the consideration of multiple axles is not a simple matter. The design may be unsafe if the tandem and trident axles are treated as a group and considered as one repetition.
On the contrary, the design is too conservative. If each axle is treated independently and considered as one repetition.
In the design of flexible pavements by layered theory, only the walls on one side, set at the outer wall path, need be considered. In the design of rigid pavements by plate theory, the walls on both sides, even at a distance of more than 6 feet apart, are usually considered.
Nowadays, the mean to measure the repetition that vehicles have at a given point on the road have advanced very rapidly. An example of this is the high-speed computer.
Yes, it helps you to consider the number of load repetitions for each axle load and evaluate its damage.
However, as a consideration, the method of dividing the axle loads into a group number is used for riding pavement designs, but not for flexible pavements. Due to the empirical nature of the designs and the large amount of computational time is required.
Instead of analyzing the stresses and strains due to each axle load group, a simplified and widely accepted procedure is to develop equivalent factors and convert each load group into equivalent 18 kips, single axle load.
Wait a minute. Are we always going to have the same equivalence factors?
No, it will depend on the failure criterion employed, especially when two different loads are present.
In summary, for a correct analysis, we have to consider the type of truck, the number of times it pays through the track, and the time of the analysis, where the equivalence of age of the axle will be developed in a general factor for the whole track, called truck factor.
However, how will this load act on the pavement?
The axle load can be assumed to be uniformly distributed over the contact area that is produced between tire and pavement. As a result, the size of contact area depends on the tire pressure.
For the pavement design, the contact pressure is generally assumed to be equal to the tire pressure, because heavier axle loads have higher tire pressures and more destructive Destructive effects of pavement. The use of tire pressure as the contact pressure is therefore on the safe side.
However, we have two ways of representing the contact area, depending on the pavement. In rigid pavement, it is formed by a rectangle and two semicircles on each side, where each width is equal to 60% of its length. In flexible pavements, we have a circle.
In other question, does the speed of the vehicle affect the load?
For this, the speed is directly related to the duration of loading, and generally, the greater the speed, the larger the modulus, and the smaller the strains in the pavement.
With respect about environment, we must consider the factors that influence pavement design, include temperature and precipitation, both affecting the elastic modulus of the various layers.
And it's not that simple. The effect of temperature on asphalt pavements is different from that on concrete pavements. Temperature affects the resilient models of asphalt layers and induces cooling of concrete slabs. In cold climates, the resilient model of unstability materials also vary with the freeze-thaw cycles. The severity of cold climate is indicated by the freezing index.
So in that case, we can correlate this freezing index with the depth of frost penetration.
Exactly. Another effect of temperature on pavement design in cold climate is the frost penetration, which results in a stronger subgrade in the winter but a much weaker subgrade in the spring.
Okay, and taking back to the difference between the effect on asphalt layer and the effect on concrete slab, we have some important difference related to the hot mix asphalt or HMA. To the elastic and viscoelastic properties are affected significantly by pavement temperature. In that way, any mechanistic methods are flexible pavement design must be considered pavement temperature, which can be related to air temperature as well.
In addition to that, we know during the winter, when temperature is low, the HMI becomes raided and reduces the strength in the pavement. However, stiffer HMI has less fatigue life, which may neutralize the beneficial effect of smaller strains. Low temperature can cause asphalt pavements to crack.
On the contrary, for concrete pavements, we have to consider that the temperature gradient affects not only the cooling stress but also the slab's grade contact.
That's why during the day, when the temperature at top is higher than that at bottom, the slab cools down so that its interior may not be in contact with the subgrade. At night, when the temperature at top is lower than that at the bottom, the slab cools upward so that its edge and corner may be out of contact with the subgrade.
The loss of subgrade contact will affect the stresses in concrete due to wheel loads. The change between maximum and minimum temperatures also determines the joint and crack openings and affect the efficiency of load transfer.
And we can forget the effects that the precipitation from rain and snow affects the quantity of surface water infiltrated into the subgrade and the location of the groundwater table.
Every effort should be made to improve drainage and alleviate the detrimental effect of water. If water from rainfalls can be drained out within a short time, its effect can be minimized, even in regions of high precipitation.
The location of groundwater table is also important. If you don't remember, the water table should be kept at least 3 feet below the pavement surface. In seasonal frost areas, the dip from the pavement surface to the groundwater should be much greater from the usually. If proper drainage cannot be provided, a smaller elastic module must be selected for the component layers affected by poor drainage.
However, the measure might not solve the problem, because poor drainage could still incur damage other than the lack of shear strength, such as the pumping and the loss of support. And if we go into details about drainage, we can talk all day long. Continuously, the material properties are of great importance in the design of both rigid and flexible pavements. The calculation of these properties help to determine pavement responses, such as stress, deformations, and displacement, in order to predict pavement failures. In this case, the elastic modulus based on the recoverable strength and the repeat loads that is called the resilient modulus.
Well, the resilient modulus is a fundamental material property used to characterize on both pavement materials. It's a measure of materials stiffness and provides a means to analyze stiffness of materials under different conditions, such as moisture density and stress level.
The resilient modulus is the elastic modulus to be used with the elastic theory. It is well known that most pipe materials are not elastic.
Well, these materials experience some permanent deformation after each load application.
I agree.
However, if the load is small compared to the strength of the material and is repeated for a large number of times, the deformation under if load repetition is nearly completely recoverable and can be considered elastic.
For this reason, we are explaining some topics. One of them is the loading waveform. In this case, the type and duration of loading used in the repeat load test should simulate that actually occurring in the field.
In this way, when a wheel load is at a considerable distance from a given point in the pavement, the stress at the point is zero. When the load is directly above the given point, the stress at the point is maximum.
In result, the stress pulls to be a Haversine of or triangle loading, the duration of which depends on the vehicle speed and the depth of the point below the pavement surface. In the mechanistic empirical methods of pavement design, a number of failure criteria, each direct to a specific type of distress, must be established.
Well, for flexibility pavement, it's general agreed that fatigue cracking, routing, and low temperature cracking are the three principal types of distress to be considered.
The fatigue cracking of flexible pavements is based on the horizontal tensile stress at the bottom of HMA. The failure criterion relates the allowable number of load repetitions to the tensile stress through the laboratory fatigue test on small HMA specimens.
In other hand, rating occurs only on flexible pavements, as indicated by the permanent deformance or root depth along the wall paths.
Thermal cracking includes both low temperature cracking and thermal fatigue cracking. Low temperature cracking is usually associated with flexible pavements.
And thermal fatigue cracking can occur in much milder regions. If an excessively hard asphalt is used or the asphalt becomes hardened by aging.
Although permanent deformation are not considered in riding pavement designs, the resilient deformation under repeatable well loads will cause popping of the slabs. Also, popping is caused by many other factors, such as types of subbase and subgrade, precipitation, and drainage. Well, we have reached the end of the road.
Thanks for listening and see you on the next trip.